I've got. You might just tilted it a little bit. Moving around. Okay. Today, the main concept that we're going to work on today is what's actually called graphing concepts. We're going to spend the next several days on this. The idea is, if given a function, not can I plot points and produce a picture. No, it's far beyond that. Can I tell you every important point on that picture? Where is it changing direction? Where's interesting things happening? And all of these require techniques of calculus. You're not actually going to physically draw things in general. Now, for a long time, we did that. Part of what you did in calculus was actually get out a sheet of graph paper and draw a graph. But nowadays, that's really impractical, right? I mean, you have technology. So why do we have to do this? And I think I was explaining that the other day to Annalise. It's, you're never going to draw a graph. Oh, no. You're going to look at a graph and have to interpret it. It is not physically possible to interpret any graph that you were not capable of drawing. Drawing is the lowest level. Interpretation is the highest level. If you cannot interpret a graph if you couldn't have drawn the graph in the first place. So we're learning all the pieces, how to use calculus to do things, and then later on we can interpret them. Okay? So what exactly is entailed here? Well, in baby algebra you graph lines, maybe you graph parabolas, maybe some other kind of sections. That's nice. But we're going to go a little beyond that. What if I have, let's say this is my graph, y equal f of x. I don't need a specific function. I just have something. It's more interesting when it changes direction and stuff's happening. Now, the easiest point on any graph to identify is that one, because all I got to do is put an x equals 0 and that falls out. Some of the hardest points on any graph to identify are these guys. I'm not even worried about those in general because usually that requires technology, because if those aren't rational numbers, you actually can't find them most of the time. So we're going to learn how to find those later. That's actually a minor thing. No, actually the most important points on this graph, probably right about here and right about here. Now can I find those by plotting points in general? Make one simple assumption. Assume they do not occur at integer values of x. Then can I find them by plotting points? Not possible. Can I guess them? Not possible. So how the heck would I find those guys? Well, at both of these points, let's say that's A and let's say that's B at x coordinate. I have horizontal tangents at these two guys. That seems reasonable. How would I know what those x values are? We got a suggestion?
Oh.
What do you think?
Are we allowed to answer if we've taken calculus before?
I guess any answer that's good is a good answer.
The slope is equal to 0, which is the derivative.
Beautiful. The slope is 0, but the slope is the derivative. So if I can figure out where the derivative is 0, let's write it out. Find where f prime of x equals 0. So in my picture, would it be safe to say that f prime of a and f prime of b are both 0? Would that be a safe thing to conclude? Because I have horizontal tangents at both of those. Yeah. And so one of the main things we try to find is where is our derivative equal to 0? Now, do you remember I said the main thing we're going to do after we take a derivative is usually to factor it first. Why? Because the most important question is where is the derivative equal to 0? Well, that's how we're going to start every problem pretty much. Where is the derivative equal to 0? Because then I can determine my horizontal tangents. This is not everything. This is just sort of the biggest first step. Okay? Now, let's back up a little bit. This graph is going uphill for a while. Flattens out, now it's going downhill, flattens out, now it's going uphill. In this portion of the graph, we say that f is increasing. In this portion of the graph, we'd say f is increasing. What about in this portion of the graph? We'd say f is decreasing. Now, if I didn't have the picture in front of me, then how in the world would I know that? Remember, the picture comes after everything, not first. How would I know that my graph is increasing or decreasing? What do you think?
if the derivative is positive or negative.
Beautiful. Did you watch this lecture ahead of time? No, it's not posted yet. F
No, I
prime
didn't.
of x in this area must be positive. All of my slopes are positive. In this region here, this will give you, probably should have changed color. Erase this for a moment. In this region here, f prime of x is also positive, which means in this region here, f prime of x must be negative. So if I can tell you where the derivative is positive, I can tell you where the graph is going uphill. If I can tell you where the derivative is negative, then I know where it's downhill, and when the derivative is 0, I know exactly where the horizontal tangents are. And that's where the graph potentially can turn around. Okay, so these are major deals. So right off the bat, if I take a derivative, I set it equal to 0, and I solve, I can find the a and the b, as long as the function I'm working with is not too complicated. Okay, we're going to stick with things that are not terribly complicated. So we have a name for these two guys here. We say that x equals a and x equal b are what are called critical values or critical numbers. Some books call them values, some call them numbers. But same thing. I can always tell who has had calculus before, and by the way, that's never a good thing, because they'll say critical points, which means the person teaching them calculus had no idea what they're talking about. A point is an ordered pair. These are values. They are not points. There is no such thing as a critical point in 2 dimensions. Critical points you'll learn about in Calc 3. 3-dimensional things, your input is a point on the xy plane, your output is a z-coordinate. Your input being a point would make something a critical point or not. A number isn't a point. A number isn't even like a point. It's just a number. So when I hear that term, I know somebody's already had calculus at least once, if not multiple times. There is no such thing in this class or the next class as a critical point. So we'll eliminate that from your vocabulary. And it does say 3 is a critical point on the xy plane. Where is 3 on the xy plane? I'm confused. I don't know what that even means because it's not a term. There are points we're going to look at. It's not there. Now, this y value here, this point right here, let's say is a comma f of a. Agreed?
Mm-hmm.
And this point here would be b comma f of b. In my picture, clearly those are highs and lows. I call them peaks and valleys. Peaks and valleys are called extrema. Now, this is kind of a strange word. We don't say extreme, we say extrema, because that allows the possibility of there might be more than one. So this is kind of a generic word that means there could be 1, there could be 10. And extrema is a y value. It's the highest or lowest y value I achieved. So f of a and f of b, whatever those values are, those would be extrema. Now, we'll introduce all the language, but most of us would say, well, this is a high point, this is a low point. So we have a really clever name. We call that one a maximum, and that one a minimum. And so we usually abbreviate those with? We eliminate all those extra syllables.
Max.
We just call maxes and
Min.
mins. This is, you'll have fun with this. Last semester in my Calc 2 class, I had 3 maxes, and 2 of them are my Calc 3 right now. I had 3 maxes, and their names were consecutive on the roster. And they were followed by min. No joke. It was max, max, min every day. I couldn't have planned that one any better myself. You know, nobody's name was critical or value in the class, but there were maxes and mins, but consecutively on the roll. I don't know how they worked that out ahead of time, but it was incredible. And in a calculus class, nonetheless, it was perfect. So we'll understand how to find all these things. So a critical value is anything that makes the derivative 0. That's the easiest way. It's not the only one, but it's the easiest way. Now, does it necessarily mean the graph turns around there?
Mm-mm.
Huh. There is a horizontal tangent at the origin. So there is a critical value at x equals 0. Does the graph turn around there?
Mm-mm.
Is there a maximum or a minimum there?
Mm-mm.
No, something weird is happening. We're going to learn about that one next day. The only place I can turn around is at a critical value. But I may not. It's possible I don't turn around, like in this case. But what if the graph did that? Or if the graph did that? Oh, then you'd say I have an extrema. The critical value is because something interesting happened there. My derivative is going to be 0, as we'll see. But I didn't necessarily turn around. So I identify the critical values, but as we're going to find through time that not all of them give me extrema. Most of them do. So there's two types of critical values, and we're going to find all of them in a minute, but we need to define a few things. So we say for y equals f of x equals c is a critical value if f prime of c equals 0, boom. I took the derivative, evaluated, I got 0, it means I got a horizontal tangent. But there is another one. F prime of c does not exist, but f of c exists. This is the evil one, which automatically makes it way more cool. There's a second type of critical value. The derivative doesn't exist at that point. It's not differentiable at that point, but the function does exist at that point. Okay, we'll look at an example of that in a moment. This one is far less common, but we're going to look at some of these today. Those are the two ways I can have a critical value. Now, it doesn't necessarily mean it's going to produce an extrema, but it's highly likely to. Okay, the extrema are only going to occur there, in other words. Okay? So let's start with something fairly simple. Okay? Let's see, I'm going to come up with something fairly easy. So let's consider f of x is 2x cubed minus 3x squared minus 12x plus 7. Okay? So I have a cubic. Now a cubic can change direction. In fact, it can change direction more than once. There's no absolute rules, but I just drew a graph of y equals x cubed a moment ago and it didn't change direction at all, did it? But I can change directions. So, here's the first thing I'm going to have you do from this day forward for every problem we look at, and you're going to do the same thing in Calc 2 and you're going to do the same thing in Calc 3. You're going to identify the domain before we start. Now, in a perfect world, your domain is always the whole number line, all real numbers. But what if I have a quotient or I have a square root, or what if there's other stuff involved? It may be something less than that. You always start by identifying the domain. And the reason is, when you're finding your critical values, they got to be in the domain. Right? It's very possible you could do everything right, you found a critical value, and it's not actually in the domain. You know, oh, then it can't be a critical value because it's a D and E. So, what is the domain in this case?
All real numbers.
All real. It's a polynomial. That's your favorite kind of problem. All real numbers. So now let's find the derivative. All right. We ought to be able to do this fairly simply. Everyone?
6x squared minus 6x minus 12.
Minus 12. I'd like to set that equal to 0, but before I do, I think I probably want to factor it. Now, if I can't factor it, can I just use my quadratic equation? Quadratic formula? Yeah, but I think you can factor this one. If I factor out a 6, it's just x squared minus x minus 2. Pretty sure I'll do my part. Okay.
Minus 2 plus 1.
Minus 2 plus 1, does that work? If I multiply that, that'll work? You all agree?
Mm-hmm.
Beautiful. And I'm going to set that equal to 0 at x equals -1 or x equals 2. So there's two x values where that equals 0. So those are my critical values. Now, I don't know about Extrema yet. We're gonna do some graphs and we're gonna bring them up on Desmos. A significant piece of the puzzle we're not going to learn until next day, unfortunately. In other words, how to identify something's actually a max or a min ahead of time, we don't quite know yet, but we will be able to figure that out pretty quickly. Now, something interesting is happening at both of those values. Okay, at both of those values, I say something interesting is happening in that I have a horizontal tangent at both of those. Now, does that horizontal tangent necessarily produce a maximum or a minimum? Well, let's see. I'm going to bring this up because back in the day, we would always just make a table of values and plot it. We'll do that because you aren't always going to have technology right in front of you when you're working on stuff. Okay, give me 1 second here. Okay. 2x cubed minus 3x. There we go. I'll bring it up in just a second. And I said plus 7. Okay, so here's what we used to do back in the day. You have your cheap calculator in front of you, and you do this. Now, what are the only points I gotta make sure I get on there? The only x coordinates I have to get on there? Probably those two, right? So, -1, 0, 1, 2. Should I stop there? You know, that might give me a graph that looks like this. Well, I think I might want to go a little bit on both sides of those so I know which way it's going, up or down. So at the very least, maybe that much. So let's try that. Get out your calculator, tell me what those y values are. I might want to do a little more. This might be enough, I don't know. We haven't done the problem yet. So I'll do my part. 7. Okay. That was my contribution. I'll do the 1 also. So that's -1, -13, so -6. -1's an easy one also. I think based on those final numbers, I think I would want to go one more in each direction. I'll show you why. Because this is going to cross the axis again, that's going to cross the axis again. I kind of like to see where that happens. Did I do that right? I think I did that right. Okay. And hopefully all of you are doing this and giving me good feedback here. Tell Matt if I make a mistake, I need to know. All right, does anybody get those numbers? Any of those? Yes, no, maybe?
Yes.
I need confirmation.
Yeah, all of that
I know.
check.
Okay. I mean, yeah, I could just be making this up. So. Now, why don't I need to keep going? Because these are going to go off forever. These are going to go off forever. And let's face it, there's a point when it's too much information. But I got the important stuff. So let's see, -3, 4. 1, 2, 3. All right. Let's say that's 40, and let's say that's -40. Kind of a crude graph, but I think we'll probably get enough. So, -3, -38, we're way the heck down here. We're -2, but only -3, so probably about right there. We're -1, we're all the way up to 15, there. 0.7, about there. 1 -6, now we're down to about here. 2 -13, whoa, now we're really far down here. 3, we're only at -2, and then 4, we're way back up to here. Now, we had horizontal tangents here and here, and looking at my graph, it's highly likely that it turned around. Now, do you see why I did a little bit of extra? It would have seemed strange to stop, up here, or to stop down here. Now, do we need to plot more points to know what's going on? What do you think? So what did the arrows indicate? I put arrows at both ends.
And it continues going.
Continues going in that direction. It means I'm saying it is not turning around. Is it possible it could turn around later and I just don't see it? Is it possible?
For this equation.
Is it possible it turns around later and I don't see it?
For this equation, no.
No, because I don't have any more horizontal tangents. In fact, an easier way to think about this, as x gets bigger and bigger and bigger positively, doesn't this number get huge? So my slopes are getting steeper. Now, as I get huger and huger negatively, I'm squaring it, so aren't these also going to get huge positively? Oh. So in other words, it's never turning around. So I don't really need much more than that. So it kind of looks like, yeah, it looks like I have a high point here and I have a low point here. Okay, so keep that in the back of your mind. Now I want to bring the graph up so we have something to compare it to. We're going to do a lot of this over the course of the day. I always tell people, never draw the graph or look at the graph before you start the problem, because it'll affect how you do your problem. You don't want to do that. Whoops. Hold on. So let me do the x. How much of the x did I use? What did I use? From negative what to what?
-40 to 40?
The x.
Or x, right? 4 to 3.
I went -3 to +4?
Yeah.
So that's all I'm going to graph. This is important, you understand this part. I'm only going to graph that much because that's all I did. Any more than that's probably not necessary. Now, what did I do for the y? Roughly -40 to 40. Oops. You're going to like this. All right, get rid of this guy. Now, this is spread out a little more than I did it, right? Does this look like the same graph we just did? Yeah, mine was a little more squished. Now, if I kept going, it's going that way forever. If I kept going, it's going that way forever. And it sure appears that that's the high point, and it sure appears that's the low point. Well, it is. I can't tell you that for certain yet today because we lack the tool. It's the main tool we're going to learn next day. Okay. I'll give you a hint. It's the way we test the first derivative to see if it's a high or low, and it's called the first derivative test, because that was the cleverest thing we could come up with. Remember, the formula that does this is usually called the formula that does this formula. And we don't have anything clever. There's no formula X. I'm working on formula 007 just because that sounds cool. I just haven't come up with one yet. Okay, so this is what we just did. Great. You always do the calculus first, come up, and then check to see, does the picture match what you said? You can't make it work the other way around. You can't match the picture ever, because all the stuff in between doesn't really make a lot of sense. Now, if I back out, and I back out too far, you see the problem? Everything interesting in this graph happened here. The rest of the graph isn't interesting. It's just going that way forever and ever and ever and getting steeper. So you generally only want to look at a small window. Now, how many actually have a graphing calculator? Okay, I love graphing calculators, but graphing calculators will never, in any conceivable context, give you the picture you want. You have to tell it what you want. All graphing calculators come with preset windows, for example, -10 to 10 in both directions. But there's graphs we're going to do where no part of the picture actually shows up in that window. The picture's outside the window. So in this case, we went -3 to +4 and -40 to 40. That's the window we want to use because that showed everything. If we went negative 10 to 10 in both directions, we would be missing a lot of this graph. It's not useful to us in that sense. Now, get rid of this for a moment. We're going to come back. We're going to come back many times today. So now the high and the low. So clearly now, this point is, what is this, 2 comma negative 13, and this one was negative 1 comma 15. So it appears that I have extrema, and the way we usually just say it is like this. The extrema, and we're cheating, we're using the fact that we can see what the graph looked like because we don't know exactly how to determine high and low yet. We will. But it appears that the extrema are at f of negative 1, which is 15. That's the extrema. F of positive 2, which is negative 13. The extrema is the y value, period. Period. The way I ask the question, I'll say, we're talking about your finances over the last 20 years, and I say, what's the most money you ever made in a year? And you say, 2020. So, well, what's the most money you ever made in 2020? You're giving me the x coordinate. What am I asking for?
Why?
Oh, in 2020, I made $5 million. Oh, now you've given me what I asked for. So a lot of times we're giving the wrong coordinates. So what's the highest this achieves? The highest this achieves is when x is 2. Well, that's a true statement, but you haven't told me anything. Oh, the highest it achieves is negative 13, which is f of 2. Now, clearly that's a high and that's a low, but you know what? 39 is a lot higher than 15, isn't it? And I'm not calling 39 the high because if I keep going, it goes up forever and ever and ever. So we have a kind of a problem here. This is the highest, but it's not the highest forever.
Local.
So there's language that we use. So here's what's happening, okay? Ron here decides to move to Giantville, where everybody's giant. But there's a community in Giantville, Hoppiton. You guys have all seen Lord of the Rings? And everybody's really, really little. So in his community, he's huge. So if he goes everywhere, you know, the house you live in, if you go both directions, several houses over, we call that your neighborhood. You're the biggest guy in the neighborhood by quite a bit, agreed? But are you the biggest guy ever? No, if you go far enough, there are giants. But in your neighborhood, you're the biggest person.
Local.
This is exactly the same as I'm describing. This is what is called a relative, or more commonly, local max. It's the highest point in its neighborhood. There's a region that if I go for a while, it's the highest point. Is it the highest point forever? No. So I don't call it, the other term would be an absolute. I call it a local or relative high. So it's a relative maximum, or most people just say local max. Same thing here. This is a relative or local minimum because it's not the smallest forever, it's the smallest in that region. Everybody cool with that? So there's 2 types of maximums. One is a local, one's an absolute. So how do I distinguish the difference? So now I'm going to give you a formal definition. The formal seems kind of scary, but it's going to match what we just said. All right, so I'm going to define absolute first because that's actually easier. So we say that for y equals f of x, let me define my function, f of c is the absolute maximum, we'll just abbreviate max, if f of c is greater than or equal to f of x for all, remember that symbol? For all x in the domain. For every conceivable number in the domain, f of c is greater than or equal to every other value in the entire domain. You notice I said greater than or equal. Just for fun, could I come back to the same height maybe later on?
Mm-hmm.
Can you think of something that has a maximum, but it happens more than once? I think you can. Can you think of something that has a maximum that occurs more than once? How about a sine wave? What's the maximum height? How many times does it happen?
Forever?
Infinitely many. But the highest height is 1. Do you all agree with that? The highest height is 1, and the lowest low is
-1.
-1. But they occur many, many times. So 1 is the absolute maximum on the sine wave because it's greater than or equal to every other conceivable y value I could get. It's equal several times or it's bigger. So greater than or equal, if it were equal, that means there's another place somewhere else where it's reached the same height. That's all that means. For everything in the domain forever, never, never. Now, if I want to change that definition to absolute min, what would I change in my definition? I'd make this less than or equal, and that's it. So the definition of absolute max is the highest y value ever achieved. I can have a tie, but it's the highest y value ever achieved. The definition of an absolute min is the lowest one. Will I get an absolute maximum or minimum in this picture? This goes forever. Is there going to be an absolute maximum? No, it goes forever. There's no highest number. Infinity doesn't stop. So therefore, I can have local. So the definition for local is similar. So we'd say for y equals f of x, f of c is a local or relative maximum if f of c is greater than or equal to f of x for all x in an open interval. A to b is an interval, not a point. For all x in an open interval around c. Can you give me an open interval around the number -1 where this is the highest? Yeah. In fact, I can go for a little while. At some point, I'm going to break free. If I can find any open interval where it's the highest point, then it's a local maximum. So the definition for local min, less than or equal to. Same thing. A moment ago, I talked about the cubic function. And I said, that one's kind of confounding. That one throws people for a loop. You know, it's strange at the very least. Let's consider f of x equals x cubed, okay? What's the derivative?
3x squared.
3x squared, and that will equal 0 when x is 0. Oh, so obviously I'm going to have a maximum when x is 0, or am I obviously going to have a minimum when x is 0? I know I have a horizontal tangent there. I know there's a horizontal tangent right there. I have to have an open interval around 0. Would you agree that no matter what interval I choose, around 0, it's neither the highest nor the lowest? There's always points to the right that are higher, there are always points to the left that are lower, so it's not a local max or a local min. It's neither the highest nor the lowest. So far, so good? Okay. Simple analogy, because we use this in Calc 3 all the time. So this morning we had a little time on our hands, so Noelle and I decided to scale Everest. We had a few minutes. So we climbed Everest, and there was a complete whiteout. You couldn't see 3 feet in front of your face, right? Everest is pretty steep. So I'm climbing. I finally get to the point where, I've reached the top of the mountain. And Noelle is coming down from the top of the mountain and gets there and goes, oh, finally, we've reached base camp.
No.
Who's right?
9.
I finally reached the top of the mountain. She finally reached base camp. Who's right?
Neither.
Neither. It's not the top, it's not the low. See, that's what I'm talking about. This, because it's not the highest or the lowest in an open interval. It's a confounding point. We're going to discuss this one a little later. I'll give you a hint. It involves the second derivative. That comes a little later, though. Okay? So if we understand this, I set my derivative equal to 0. Everything was good. But I said there's an evil one. Let's look at the evil one, because sometimes they're way more fun. So what do I mean by the evil one? I mean the one where the function exists, but the derivative does not. Now, that's crazy. But we have a few of these. Let's consider the following. F of x equals,
Absolute.
no, not absolute because this can't really take derivatives. Piecewise functions we tend to stay away from here because you can't take derivatives of them cleanly. So let's consider the cube root of x squared. So first thing is, what is the domain of this? The safest way to think about domain is always the same. Always start with all real numbers and then ask, are there any restrictions? For example, if I had an x in the denominator, that'd probably be, I can't use 0 or something like that. So start with all real numbers. Are there any values that I cannot put in there? I'm squaring a number and then I'm taking the cube root of that number. Can't you take the cube root of any number? So are there any restrictions? No. That's a good thing. So my domain is all real numbers. Great. So I shouldn't have any problem. So what's the derivative? Probably safer to look at this as x to what power?
2/3.
To the 2/3. So my derivative would be 2/3 x to the negative 1/3. That's a negative exponent, so it should go downstairs. How about if I just put it back under the cube? Would that be legal? Okay. At every point on that graph, the derivative is this, so I can tell you the slope of the tangent line at every point on that graph. So this will equal 0 where? Anybody?
X is
The quotient can only equal 0 when the numerator is 0. My numerator is 2.
Never
So when will this be 0?
Never.
Never. Huh. So what does that mean in simple English? There are no horizontal tangents. But the denominator has a problem. At 0, the denominator's 0. So this is undefined at x equals 0. That's what makes it a critical value. The first derivative does not exist at x equals 0. I can't evaluate the derivative at x equals 0, but x equals 0 is in the domain. That's the other kind of critical value. I call it the evil one. They're actually way more fun to work with. I don't get a horizontal tangent. It's not even like a horizontal tangent. So what is it? We went over this a couple weeks ago. Remember the name? You can cut your finger on that, it's so sharp. It's called a cusp. Good. Does my graph change direction then?
yes.
Yes. So I have an extrema at the origin, don't I? I have a critical value, x is 0, not because I have a horizontal tangent, but because the derivative didn't exist, but the function did. I'm defined there, but there's no derivative there. And I think it's pretty obvious that I have a minimum. Is my minimum going to be absolute or local?
Absolute.
It's going to be absolute. There's nothing lower than this. So we'd say that f of 0, which equals 0, is the absolute minimum. We love it when we have extrema that are absolute. You don't have any control over that. You're just locating them. Now, a lot of graphs we already know ahead of time if they're going to have absolute maxes. A sine wave will have absolute. How about a parabola? If I have an upwards opening parabola, am I going to get a maximum? No, but will I get a minimum? And where will it occur? Well, in one parabola it'll occur at the origin, but the other infinitely many it won't. It'll occur at the vertex, yeah, which is probably never going to be at the origin. But if it was, then it'd be there. So what if it's a downwards opening parabola? I'm going to get an absolute maximum occurring at the vertex. Now, we did a cubic a little while ago, and that's the most common shape of a cubic, one that changes direction a couple of times. I'm going to get a maximum and a minimum, but neither one of them are going to be absolute. I don't need to know what the function looks like. So I'm going to go back to this guy. I think I still have it up here. No, I'll put it back up here. My original function, I think it was 3x squared, and was it 12?
Yes.
Okay. I want you to tell me, without doing any work, we're starting this problem for the very first time. We haven't even taken a derivative. Tell me why I cannot have an absolute maximum. Well, because I already looked ahead on Desmos and saw what it looked like. No. It's the first time in your entire life you've seen this combination of symbols. Never run across this in your life. As x grows without bound, tell me about your y values.
Also grows without
They're growing without bound. You're done. There's no absolute maximum. That's it. That's not calculus. As x grows without bound, this is going up forever. Now, what if x goes negatively without bound?
Well, then, negative.
It's going to go down forever, isn't it? So there's no absolute minimum. That's only to determine if it's absolute. So as we go along, you're going to learn how to determine if something's a max or a min in general. But you won't know if it's local or absolute until you go back to the function and say, oh, there are no absolutes here because it goes up forever, so any max would have to be local. There's no absolute min because it goes down forever, so any minimum would have to be local. It's actually that simple to make a conclusion. I do not ever have to know what it looks like. That's kind of nice. Now, why did I only look at the lead term? Now, this is something that I think we did once before in class. I apologize ahead of time because sometimes I forget what I showed you guys because I may have shown that thing to my Calc 3 students instead. The reason if you have a polynomial you only need to look at the lead term to determine behavior is because you can factor the lead term out. Remember this? If I wrote this like this, this is not in the textbooks. This is the simplest explanation there is. Is this true or false, this statement? True. So as x gets bigger and bigger and bigger, do these guys contribute in any way to the shape? No, they're all transient terms. As x gets bigger and bigger and bigger, only the 2 is contributing because all of these guys are going away. They're going towards 0. Oh, and then if x is getting more and more negative, it's the same thing. A lot of folks will say, well, wait a minute, but this one's also getting infinitely big, and it's getting infinitely big in the opposite direction. Don't they kind of cancel? For small values of x, they do kind of cancel, don't they? But as x is getting bigger and bigger and bigger, if x is a million cubed is a lot bigger than a million squared. Or another way of looking at it is it produces a bunch of transient terms. This is the craziest part. As x gets bigger and bigger and bigger, can I say that this is asymptotic to 2x cubed? It is never equal. There's no value of x where they're equal. But as x gets bigger and bigger and bigger, another way of saying that, if I evaluate this at a very, very large value of x, I'm going to get a huge number. If I evaluate this at the same value, I'm going to get a number that's really similar. And it's really easily evidenced. This is why I love Desmos. I need to change this back to where it was before. Okay. I love doing stuff like this. Okay. Oh, that did not do a cube for me. There we go. Okay. The concept of asymptotic convergence, most Calc 1 classes don't talk about this much, if at all. And the thing is, you need to talk about this because almost all the information you're going to learn for the rest of your life about this, you learn in this class. You're supposed to know it later, but you're not going to see it later. So, the red graph is our original graph. This is just y equal 2x cubed. They're completely different graphs, obviously. So I want to back up. I want to back up. I want to way back up. I want to go out there. I want to keep going back there. I want to get farther and farther and farther and farther away. To the naked eye, what are you seeing? These graphs are merging into one. Why? Because the difference between them is getting smaller and smaller and smaller. Do they intersect? Only do. Origin. Well, actually, they don't even intersect. They intersect somewhere, at one point, they intersect somewhere in here. Who cares? I'm talking about what's happening forever. As x gets bigger and bigger and bigger, I can't tell the difference in the graphs. And by the way, look at the y, look at the x values. I mean, by the time we're literally to -10, by the time we're to -10, you can't even tell the difference in the graphs. That's not even, you know, -10 is not very big compared to infinity. Now let's zoom in again. They intersect at that one point, but then they quickly approach each other. That's why we can say that the 2x cubed is asymptotic, which means they have similar behaviors. So you're doing something large scale. When do you do things that are large scale? Chemistry and physics. In chemistry, you work with things that are really small, infinitesimally small. Right? You don't write answers in decimal form. You write things in scientific notation. Why? Because your starting point is usually on the order of what? 10 to the
Whatever.
-23rd power. Oh, now there's the size of an electron. Oh, and in astronomy, you're talking about astronomical distances, things on 10 to the large exponents. You're not interested in the smaller numbers. So in this sense, you're not even working with all the numbers, you're just working with the extremes. So understanding this concept of asymptotic behavior, that when you're dealing with really large numbers, you don't necessarily need all the other pieces. If you've had statistics or you want to take statistics, statistics is the study of asymptotic behavior. In the low level, we don't talk about it. But the idea that I'm going to use a sample to make conclusions about a population, the limit of the sample becomes the population. Oh, so they become equal based on a limit. That's why the squiggle is appropriate. They are asymptotic. But I can use small things sometimes to make predictions about big things without having all the pieces of the puzzle necessary, because I know how things are behaving. If I had to, for example, this function we just did, the red one, I want you to evaluate this by hand at 1,000. You could do it. It'd be astronomically big. 1,000 cubed, by the way, is 1 billion. So on this graph, it would be 2 billion. What would the y value be on this graph? Let's do it. I mean, we have calculators. So I want to go 2 times 1,000 cubed minus 3 times 1,000, by the way, when you're talking infinities, 1,000 is pretty small. Minus 12 times 1,000 plus 7. That answer is 1,996,988,007. Just a hair below 2 billion. On the other one, it was exactly 2 billion. The difference is less than 1/10,000. Or in other words, the difference is less than 1/100%. And that's when x is 1,000. What if I replace x with 1,000,000 or 1,000,000,000? The difference now is, you know, a lot of zeros after the decimal place, percentage. That's why we would use the number on the far right if we had to do a quick calculation, because it's going to be almost the same for all practical purposes as the number on the left. Again, the concept of asymptotic convergence. So this is going back to, I know this is growing without bound, I don't need to look at the rest of it. I know it's growing without bound, I don't need to graph more than regraph by hand. Everybody cool with that? Now let's do something a little bit more complicated. I'm going to leave this here. Only because I can't trust that I can stop this every time. No, it's not stopping this time. Shouldn't be tempted fake. Okay. Now, what I'll do is, I know one of the instructors I work with, they just don't even bother pulling it down. They just do everything on the board. I might be able to get away with that. Okay. We're going to do a completely different problem, and I'm going to turn this off for a moment because I need the board. I need all the space. Now we're going to do one that's a little bit trickier. Okay? I would like to consider and find any critical values of the following. Let's say okay, we want to consider this guy. The fractional exponent automatically makes things more interesting. I'm more likely to have strange things happen. Okay? Are there any restrictions on this graph? We just did a 2/3 a moment ago. We said it was all real numbers. I'm multiplying by x minus 5. There's no quotient. There's nothing weird. So I think we're okay with the domain in this case being all reals. Everybody okay with that? I need to take a derivative, but I don't want to take a derivative in that form. We said after you take a derivative, you always factor your answer. You set each piece equal to 0. But if I had wanted you to take a second derivative of something, let's say the first problem we did, for whatever reason, I needed you to do a second derivative. Would you take the second derivative? Would you do the derivative of the polynomial or the factored polynomial?
Factored polynomial.
Hopefully it's a no-brainer. Do you want to do the derivative of the polynomial the way it was or the factored polynomial?
Right, sorry.
Polynomial.
Yeah, because you're done in one step. The other one you've got to use product rule, combined terms, it's extra work. Why would you don't want to differentiate the factored form of anything ever if you can avoid it? I can differentiate that. Or I can do what? Distribute. In which case, now the derivative is one step. Always do that. Having said that, most of you will differentiate the factored form and maybe make a mistake. Note, the factored form is far more useful if I want to evaluate it, if I want to actually figure out where points are. The factored form is easier to work with. But for differentiation, I'd rather differentiate that. It's easier. So what is f prime of x?
Uh, 10.
Don't dare volunteer an answer. You might be wrong.
Minus 10
Thirds.
thirds.
How about 10/3?
-1.
Negative 1.
Right now, these exponents differ by exactly 1, so they still differ by exactly 1. I need to keep that in the back of my mind because I want to factor. What is common to both terms?
3.
Right?
Oh.
How about 5/3? X to the
Negative 1.
-1/3. But we just said these exponents differ by exactly 1, so that should leave a whole x. If you want to multiply these back together, okay, good. Minus 2. That wasn't terrible. So this clearly equals 0, add x equals 0, or x equals 2, right? I'm winking with my left eye. You guys know what that means, right? It means I'm pulling a fast one on you. It's clearly equal to 0 at 0 and at 2. Some of you are shaking your head.
No, just 2.
What's happening at 0? Oh, I got a negative exponent here, which means I probably am a little premature here. I have a better idea. Might change our answer slightly. How about we rewrite this as 5x minus 2 over 3x to the positive third. Or you could put cube root. Is that the same thing?
Mm-hmm.
Now, where does this equal 0? Well, obviously at x equal 2, oh, it definitely doesn't equal 0 when x is 0. What's happening at x equals 0? It's undefined. Oh, I'm going to put und. That's quite a bit different. If the derivative equaled 0 somewhere, I have a horizontal tangent. My derivative is undefined there, but isn't 0 in the domain?
Mm-hmm.
Simply, that means you have a vertical tangent there. Oh, that is cool. Remember the cusp we just did a moment ago? It might be a cusp, it might not be, but I have a vertical tangent there. That I do know. By the way, is 0 still a critical value? Yes, because it made my derivative not exist, but it was in the domain of the function. So I have two very cool values there. I know what's happening when x is 2. I'm going to have a horizontal tangent. I don't know what's happening yet at x equals 0. That's going to be more interesting. We'll figure that one out in a moment. Okay, so far so good? I said this was going to be a little more interesting than the last one. So then, let's graph some values, okay? There are a few gimmies here. For example, would x equal 0 be a gimme? How about x equal 5? Would that be a gimme? There's a couple of gimmies here. And anything that makes it a perfect cube would probably be a good one, okay? So maybe I probably don't need to go much to the left. I'll just go -1. And then 0, 1, 2, 3, 4, and 5, because all those are going to be below the axis. Maybe I'll just go one more. I'll go 6, because I want something on the other side. And some of these are going to be easy. Now, I'm plotting points. I don't need 10 decimal place accuracy. 1 decimal is probably more than enough. So let's take the gimmies. When x is 0, this is 0. When x is 5, this is 0. Agreed? How about when x is 1? If it's 1 times -4, I'd say that's a gimme. That was the last gimme. Everything else is going to be a decimal. Okay, so let's do the rest of it. So when x is 6, I have 6 raised to the 2/3 power times 1. That's about approximately 3.3. I don't need more than that to be accurate here. Okay? That's probably good enough. Well, we're going to do this one again next day. We're going to go a little further. How about when x is 4? Then I have 4 raised to the 2/3 power times -1. That's approximately -2.5. And 3, so I have 3 raised to the 2/3 power times -2. That's approximately -4.2. And then finally 2 raised to the 2/3 power times -3. That's about -4.8. And then -1's an easy one, because -1 to the 2/3 is +1. Then times -6. I think that looks about right. I think we have enough there that we can work with. Does it change direction? I'm not really sure yet. I'll do it over here, because I'm going to use this space in a moment. How much did we go to the left of the y-axis? Just 1 unit. 1, 2, 3, 4, 5, 6. And vertically, we didn't go very far. So 1, 2, 3, 4. Oh, we went a little farther down. Here we go. So 1, 2, 3, 4, 5, 6. All right. So -1, we're down at -6. Okay. At 0, we're at the origin. At 1, we're back down to -4. 1, 2, 3, 4. At 2, we're about -4.8. At 3, we're about -4.2. At 4, we're about -2.5. And then at 5, we're back to 0. And then here, we're up here. Okay. And that's going to keep going, isn't it? That's going to keep, I don't have a horizontal tangent at 0, but we said we had a critical value at 0. What do you think it is? Based on what we did earlier. What do you think's happening here? Wait, it has vertical tangent, but what is that thing called? You cut your finger on it? The cusp. Yeah, I got a cusp here, don't I? Did we graph enough to have a pretty accurate idea of what's going on here? Yeah. Do I have an absolute maximum in this problem? You're looking at the picture and you're going, I don't think so. Do I have an absolute minimum in this problem? You're looking at the picture saying, I don't think so. Could you have told me going back to here? Yeah. X to the 2/3 is never negative, agreed? Because I'm squaring something. As x grows without bound, that's growing without bound positively, that's growing without bound positively, it's going forever up. As x goes negative forever, This is growing without bound positively, but this is growing without bound negatively, so it's going down, positive times negative. I could have figured that out without drawing a single point. Now let's look at the desmos. We're only going to look at this one thing. Oops. There we go. And this guy. If it doesn't let me do it, I'll just erase this. Well, Desmos doesn't want to read the. Boy, this was doing great for the longest time. Oh well. Okay. I think we'll still be okay. Now, this is more information than I need. What did we just graph from? Did I erase it already? We graphed from -1 to 6. So that's what I'm going to do. I'm going to go here. X is going to go -1 to 6 because that's all I need. And if you had a graphing calculator, I would hope that you'd do the exact same thing. Only use the stuff that you graphed from. My y values went to about -5 almost. And in the other direction only went to about 3.3, so I'll put 4. This is pretty much what we just drew. That's cool. Okay, I'm going to show you something even cooler than that. You see two things meeting, and it looks like they're meeting at an angle. So here's what I'm going to do. I'm going to blow this up. Remember that angle they were meeting at a moment ago? What do you notice?
Getting narrower and narrower.
It's not, it doesn't look like it's meeting at an angle anymore, does it? Does it look like it's meeting at an angle? When we drifted out, it almost looked like there was an angle there. This is one thing you have to understand. When you graph this on your graphing calculator, it might not even show that it's intersecting at the origin. It might have it lower because of the way it calculates using pixels. It's kind of odd. It's very old-fashioned. But as we zoomed in, can you now see the vertical tangents? It clearly looks like it's getting vertical on both sides. But when I was way the heck out here to start the problem, it clearly, whoa, too much. Okay, probably overkill here. Sorry. I got a little carried away there. Okay. Oh, this is not helping me. Changed my, oh, what the heck? Okay, let me leave that alone. It changed our scale a little bit too much. As I zoomed in, it looks vertical. That's important to understand that. When I'm drawing this, any way you represent a cusp, it's just fine. A cusp is not the only time you're going to have a vertical tangent. There's one other situation, okay? And I want to talk about that one. We're going to take a break in a moment because in the second half we're doing something slightly different. I'm going to throw a what if at you. We've done this one before. Okay? Some of the stuff we look at, this will be embedded in the problem, in other words. Do you agree that the domain is all real numbers? Nothing I can't do. Actually, let me call it f of x. It's easier to do the notation. So this is x to the 1/3. So what is the derivative? It would be 1/3 x to the -2/3, which is 1/3x to the +2/3. We just said a moment ago, we believe the domain is all real numbers. This is never 0. But is it undefined anywhere? Where's it undefined? At x equals 0, yeah. Undefined at x equals 0. That means 0 is a critical value because it made the derivative not exist there, but the function did. F of 0 is 0. That's not a problem. But f prime of 0 does not exist. You don't say it's undefined. No, it doesn't exist. There is no derivative at 0. So what's happening at 0? Well, technically this is the inverse of y equal x cubed. So if y equal x cubed has a horizontal tangent at the origin, this ought to have a vertical tangent at the origin. Looks like this. Now, it's a very subtle difference between a cusp and a vertical tangent. And this, we just say it's a vertical tangent. We don't say it's a cusp, it's a vertical tangent. There's a very subtle difference. I'm going to show you what it is. Because sometimes you won't be able to tell by looking at the original function. You got to do your derivatives. You got to look at things. Oh, what if I just, what if I took this piece and I flipped it over? Like that. I took the mirror image. And that would be a cusp. The difference between a cusp and the vertical tangent here is if I, so in the previous problem, what was our previous one? It was this. If I had taken this piece and flipped it over, I'd have the vertical tangent. Does that make sense? So when do you see this phenomenon occurring? Generally only when you have fractional exponents. And the reason is, particularly a fractional exponent that's between 0 and 1. Because after one derivative, that exponent became negative, which now meant you were undefined somewhere. That's kind of cool, though, by the way, think about it. So if I said, let's deal with square root, let's deal with cube root, let's deal with the 3/4 power. Any fractional exponent between 0 and 1, my first derivative, I'm going to have a negative exponent. Which means it's very likely I'm going to produce one of these types of things, depending on the domain. Everybody cool with that? Okay, this is probably a good stopping point. Would you go ahead and do that?